So far in this unit, you have studied how to display and describe categorical data. Specifically, you made some bar charts and pie charts, and you made frequency tables and relative frequency tables. What we're looking at next is an example of what not to do. So here's a picture of a misleading graph, also called a truly unfortunate representation of data. And the reason that this graph is not a good graph is because it violates the area principle. When we look at this graph, it looks like a lot more of the passengers on the Titanic were crew members. However, we're not sure whether we're looking at the length of the ship or the area of the ship, so it's quite confusing. Next, I want to take a look at contingency tables with you. You did something like this in our opening activity where we compared the favorite toys versus male and female. And then what we've added on here is some extra information on the totals and the subtotals. So all that this contingency table does is it gives you a little bit more detailed information. So for example, that you can tell that of all the passengers on the ship, 706 of them were third class out of 2,201. Or you could tell that 167 of the passengers that were second class perished. So there's lots of information you can get from a contingency table. One last example I want to show you is an example of Simpson's paradox. And Simpson's paradox is when something kind of unexpected happens. And you'll see what we mean here as we work through this problem. So in this scenario, you are a baseball coach and you're trying to decide which of two players you're going to put in as a pinch hitter. You've got player A, who in his last 103 at-bats, he got a hit 33 times. And player B, out of his last 151 at-bats, he got a hit 45 times. So if you know anything about baseball, you know that we look at batting averages and we will divide these numbers. So player A has a batting average of about .320, while player B has a batting average of about 298. So at this point, looking at this overall data, it looks like a no-brainer to select player A as our pinch hitter. However, when we add in a little bit more data, maybe we care about whether the pitcher is left-handed or right-handed. When we start to look at that data, we see some more interesting information here. So our overall batting averages have not changed. And in our overall batting averages, A was the better player. They had the higher batting average. Now, if we go and look at left-handed pitchers, the batting average for player A against left-handed pitchers is .346, and for player B, his batting average against left-handed pitchers is about 3.375. So that's kind of interesting, in that if I were going to be putting in my pinch hitter against a left-handed pitcher, I might want to pick player B, even though his overall batting average is lower. Now, let's go ahead and also look for right-handed pitchers. And we'll see that player A got a hit 5 out of 22 times at bat against righties, and that's an average of .225. And player B got a hit 33 times out of 119 times, and that's an average of .277. So again, player B outperforms player A, this time against righties. So what's interesting is that based on this information, it appears as though it's more difficult to hit a right-handed pitcher, and player B is used a lot more frequently against right-handed pitchers. So that average is dragging down his overall average. So even though player B does better in both types of pitchers, his overall average ends up looking lower. So in reality, if you were the coach, it's a paradox. You should pick player B, the one with the lower overall average.